All right. Thank you, Ted. So this probably won't be super surprising to anyone. Just I give a usual spiel before most of our meetings just to kind of lay the expectations out of how these book clubs typically run. So we're the San Diego Machine Learning Group. This session, we're going to be looking at the Mathematics for Machine Learning book. Right, that this session will be looking at chapter 2. And so the goal of this right now is just to discuss the format, so understanding how this is going to be run and also set expectations. So in the past, we've run things in certain ways, and I'm just going to kind of lay out what to expect for this reading of this book. So for today, we're just looking at the format, setting the expectations, and then we'll also be discussing chapter 2, which was linear algebra. So the format, what we want for this session is we really want people to read ahead. So in the past, we've been kind of lax on that. We're not going to punish you if you didn't read, but we do want you to read ahead of time because this is technical stuff and we won't be able to teach the entire thing in an hour span. So the hope is you read it beforehand and then you come here and you can ask questions and we can work through problems and go through the actual details that people didn't understand rather than going from zero and trying to teach the whole thing in an hour. So just understand that it might be a little bit differently than we did in previous sessions where we kind of devolved into we're just going to teach the whole chapter every single week. So just a few tips. So the whole point of this group is that we can share knowledge. And so if you read something and you don't understand it, give it a second read, give it a third read, but don't stress over it and just come here, ask a question, and then maybe someone can unlock that knowledge for you rather than you trying to synthesize it yourself. If notes are useful for you, take notes. That's always powerful to get it to stick in your brain better. And also bring questions. So if you go through the book and you say, oh, I didn't understand this, or this problem was particularly hard for me, can someone explain why this certain case is true? Then definitely write it down and remember it for the next session so that we can discuss it. And the last piece is this is a social group. So a lot of the value out of this is just meeting the other people that are here, local to San Diego or remote. They might be able to offer you a job. You might be able to get a job. There's all different values to just being connected to the people in the community. So back in school, I was definitely one of the more quiet people, but I found value in speaking up and actually participating and meeting the people around you. So I encourage everyone to try to do that. So we have a Slack channel. If anyone wants to go there, you can go introduce yourself in more detail. So we already did a few minutes of introductions, but if you didn't get a chance and you want to introduce yourself, you can go over to Slack and say, here's who I am, here's where I'm from, here's what I do. And that's good to see where everyone's coming from and what value they might provide or what they might want to learn. That's good feedback for us. And with that, I will hand it over to Liam, and he'll be talking to us about chapter 2.
Hi, thanks, Ryan. So my name is Liam, and I'm relatively new to presenting in this group, but I have compiled a presentation for chapter 2. And let me see if I can start it here. One thing that I just want to add on to that is that I just think about it like, we're getting a lot of value actually from reading through and doing the exercises and then compiling these into presentations. So, if we're getting that kind of value, you might as well get that kind of value too by, completing the exercises and diving into it deep. As Ted was saying, it's kind of a difficult thing to just digest yourself, which is why this group is to sort of discuss the finer points of it. A little bit about me, I actually come from a software engineering background and not necessarily a very heavy math background. So this is, my opportunity as well to kind of dive deep into these concepts. And, obviously Ted and Ryan will keep me honest, so we're not going to mislead you or anything. But so if there's any additional insight or any topics that you have something to add to, I'm sure that everybody in the group would be interested to hear those insights so we can discuss it and, expand our own perceptions of the material. So with that in mind, I'm going to start off with linear algebra. So this is chapter 2 of the Mathematics for Machine Learning textbook. So basically, the first thing that and primary base for the rest of the chapter in linear algebra in general are systems of linear equations. And I actually just realized I did not take out my notes, so give me 1 second. Sorry. Technical difficulties. Yeah, so basically, I would assume that most of us have seen systems of linear equations, multiple equations used to describe the same, system. This particular series of equations has 3 features or 3 unknown variables, x1, x2, and x3. It also has a sequence of coefficients. For instance, in the first equation, it's just 1, 1, 1, and in the second one, it's 1, negative 1, 2. And then it has a series of outputs, which in this case is 3, 2, 1. Basically, this can be rewritten in matrix form, where on the left, you have the coefficients, and on the right, you have the actual variables themselves. And then multiplied together, you get the output, which is 3, 2, 1. But as you might be able to tell, I haven't really defined what multiplication is yet. Multiplication, in this case, is, the formatting is really weird for some reason. Anyways, so matrix multiplication here is basically if you have, and that's math notation for A is a matrix within the space of m by n real numbers. In the book, you'll see R is a lot more fancy, but in this case, I used bold because it's the closest to it. Epsilon is contained within. So you have an A, which is an m by n matrix, and B, which is an n by k matrix, where the columns of the first matrix are the same number as the rows of the second matrix. And so we can define A times B is equivalent to C, which is a matrix which is m by k. It takes the number of rows from the first matrix and the number of columns from the second matrix. So in this case, it's 3 by 1. And basically, each element in C is the sum of the corresponding row multiplied by the corresponding column. So if you look at the first row of the first matrix 1, 1, 1, you multiply 1 times x1 plus 1 times x2 plus 1 times x3, and on the right hand you get 3. So, and then you go down, so it is equivalent to that system of equations. In this case, as you might be able to imagine, AB is not equal to BA. So that means that matrix multiplication is not commutative. And I'm going to get into the properties in the next slide so we can have a good baseline there. But so if you were to move the x's to the front, then of course you wouldn't have the appropriate dimensions to actually multiply them together and it to make sense. So another example is this. So as you can see, we have m rows of the first matrix, which is 2, and k columns of the second matrix, which is also 2. And so you get a 2 by 2 matrix as a result. The first, row and the first column, that value is 1 times 0 plus, 0 times 1 plus 2 times 1 plus 3 times 0 for the corresponding row and the corresponding column. And so you get 2. And then you do the same thing with the second column and you get 3. And then you go down to the second row of the first matrix and do the same thing and you get 2 and 5. 0 times 3, 1 times 2, 0 times 1 is 2, etc. Hold on. Sorry, give me 1 second. I'm sorry, the version of OpenOffice, I think, is different than it is on my personal computer. Okay, so I don't necessarily know why that's not appearing, but so you have basically, I'm defining matrix addition here. So if you imagine that the first matrix there is A1, A2, A3, and A4, then plus the matrix of B's is actually element-wise addition. So the first element is A1 plus B1, the second element is A1 plus B2, and so on. And the last thing I want to define here is multiplication by a scalar. And a scalar is basically just, it scales the matrix. It's any real number. It can be a flotation point, doesn't really matter. You can write it as, lambda, and then use that epsilon character, and then put R to be the set of real numbers. So it is within the set of real numbers. But yeah, so you just do it to every element in the matrix. So some of the properties that I want to list here are commutativity, which is something we just talked about. In this case, multiplication, I'm using multiplication to denote this, but it doesn't actually have to be multiplication. It can be any operation. So this can be plus, this can be, scalar multiplication. There's a bunch of stuff that this could be. But right now we're thinking about it as multiplication. So commutativity is A times B equals B times A. Pretty simple. Associativity is basically, it doesn't matter which.
Hey, Liam?
Yeah.
Sorry, just to interrupt. You might want to clarify this is properties of the group.
Only if it's abelian, right? Only if it's only commutative. If it's an abelian group,
Okay,
right?
so sorry, I'm just not sure what properties of what that you are listing here.
Well, I was just doing properties of like sets in general.
Okay, sorry.
Well, actually, no, that's a good that's a good distinction to make. Properties of just sets of things. We can talk about like matrices. We can talk about like real numbers, etc. Properties of sets. That's fair, right? Okay, yeah. Sorry about that. So associativity basically means that like it doesn't matter which order you do the operations in. So you could do A multiplied by B first and then multiplied by C, or you could do B times C first and then A, or something like that. And then distributivity is actually for two operations. So in this case, I'm using fancy plus, but let's just call that addition for a second. So basically, A times B plus C is the same as A times B plus A times C. So in this case, we say that multiplication is distributive over addition. So that's just like two operations. And then we have closure, which that upside down A means for all A and B, which is in a particular set, A multiplied by B or A operated by B is also within that set. And that becomes important later on when we're defining groups and stuff like that. We also have the identity or the neutral element. So there exists a value E, that's what that backwards E is. There exists a value E that is within the set S that for all A, which is also in that set of S, A times B equals A. So basically in a set of real numbers, this would be 1, and in matrices, this would be the identity, but we'll talk about that in the next slide. And the last thing I want to talk about is this idea of an inverse. So for all A in S, there exists a B in that same set of S, where A times B equals B times A, and that equals that identity element. This also means that, like, say if you have B times A on one side of the equation, you can, there's an inverse operation that you can do to move B to the opposite side of the equation. That's how I like to think about that. So as far as matrices go, we have this thing called the identity matrix, and this is the basically the equivalent of 1 in matrix terms. And you can kind of reason with that. Like, imagine if you're multiplying this by a matrix, then the only thing that's going to be returned by the first row, first column is the first row, first column in the matrix itself. So multiplying something by the identity matrix with the same number of rows or columns is going to equal itself. So this is the identity element. There's also a transpose, which basically you just flip a matrix to the side, or its rows become its columns, which is pretty much all you need to think about that. And that's denoted by, like, say, a to the t. So that's how you denote that. So flipping it to its side, it means that it is distributive over matrix addition, but it's not quite distributive over matrix multiplication. Because you flip the dimensions, you actually also have to flip the order in which the matrices are multiplied by each other. So AB transpose is actually equal to B transpose times A transpose. And then this is getting cut off because it's a different version, apparently. But to square each element in a matrix, you actually multiply that matrix by its transposition. And if you want to think for a second about why that is, go ahead. But yeah. So the last thing is the inverse. There is such a thing as inverse. However, not every matrix is invertible, also known as regular or non-singular. Also, in order for A to be invertible, it needs to be a square matrix. So basically, and you can imagine that because A and its inverse need to be have the same dimensions, and they equal I, which is the identity matrix. So it needs to be square, but not all matrix is invertible. So basically, in this case, it's actually not distributive. And it's also, it's not distributive over addition. And again, it's kind of not really distributive over multiplication because you have to flip the order again. So yeah. So how do we solve systems of equations? And I hope that this formats correctly. Oh boy, okay. So first you want to find the particular solution. So as we noticed beforehand, we rewrote that system of equation in AX plus B. And A, we're going to call that matrix with all the coefficients. AX equals B, and that's going to be the output. This is an inhomogeneous system of equations because B is not equal to 0, pretty much. And so we can actually rewrite that in this form, and we're putting B on the right side and A on the left side, right? Just to make it clearer, we don't actually care about writing down the X at this point. We then use something called Gaussian elimination. And of course, there's algorithms that do this faster, but actually solving this by hand makes it easier to understand what is actually going on here. So we reduced that to something called row echelon form. And basically that looks like something like this. So the first non-zero entity of each row is 1, or else you can reduce it more. And it's always to the right of the row before it, right? And so you can actually get there by, you can swap some of those rows. You can add a row to another row. You can subtract a row from another row, and you can multiply rows by a scalar. So eventually what you can do is you can simplify it into row echelon form by doing that. So you can use that to actually solve the system of equations and get values for x1, x2, x3, x4, x5. You can do that by, if you look at row 3, right, that means that if you have x4 and x5 at the very end, 1x4 minus 2x5 equals 1, x5 must equal 0, and x4 must equal 1. You can solve for the next one and the next one, etc. And the last thing I want to mention about this is that the first non-zero entry is called the pivot. So in the first column of that row echelon form, that is a pivot column because it is 1. The second column is a non-pivot column, and we'll be getting into why that's important later. But just keep that in mind. And also the last column, column 5, is not a pivot column. So we can then use that to create a general solution.
William,
yes?
Before you go on to the general, we have a question in the chat. Can all matrices be reduced to this row echelon form?
Yes, right? Yeah. All matrices can be, well, you can, you can use these steps to reduce it to a row echelon form. I think, well, there would be an edge case, right? If it's like, if all of them are non-pivot columns or something.
So you actually have a great example of a slightly unusual where you see all zeros in the bottom row. So that's one of the things that can happen, but there always will be a row echelon form, no matter what matrix you start with, and no matter what the shape. It can be square, it can be tall and skinny, or fat and wide, but it'll always have that form.
Yes. Yeah, totally. Well said. So a general solution, the way I like to think about that is, so we have these columns, right, that are non-pivot columns. So basically that means that, that second x2, that's not important to the solving the equation at all. So what we can do is, we can actually find a series of coefficients for those x values that equal 0. And if it equals 0, then we can add it as many times as we want to the system of equations, and it doesn't actually change the output at all. So the number of solutions where AX equals 0 is actually the number of non-pivot columns, because those columns don't depend on, any of that. And we'll get into more complicated as it gets. This is actually considered the basis vectors of what's called the null space. So we have that particular solution at first, and then we say
Liam,
plus
can you please point on screen?
some lambda or scalar, it doesn't matter, you can multiply it by whatever you want. And then the first solution of AX equals 0, and the second solution of AX equals 0. And so then that's the actual general solution with the null space.
Can you please point on the screen?
I don't know if on your old laptop the mouse works well for you to be able to point to which, as you're going through slides, to point to which parts of the slide you're talking about.
I think I can actually.
Yeah, it'll show up in the Zoom.
Okay, yeah. Was that it? Okay, cool. Yeah, I'm happy to do that. So we're going to take a step back, right? And we're going to talk about groups, right? Which is something that we alluded to a second ago.
So before we get into groups, now might be a good point to pause and just see if there's any other questions about systems of linear equations. Obviously, we haven't gotten into some of the more advanced stuff, but still at this point, just to...
No, actually, that's a good idea. I was thinking like, we could stop for questions at some point. And actually, I was thinking right after groups.
Okay.
But no, let's do it now. I think that's a better idea. Yeah. Yeah, we can stop for
There's
some
a
questions.
request to go to the last slide.
Give me 1 second. Yes, there. Okay. And what was the question? I can't actually see the chat at the moment. Any questions?
Is there a significance of having that last row of all zeros? Like, does that tell you anything about the rank or anything?
No, not really. I mean, this is just how this particular system of equations was solved. Most of them, as Ted mentioned, don't actually have that last row being 0. It's just that we found that the last row doesn't contribute significant information to solving the system of linear equations. And that's, yeah, so.
But
yeah.
you can use this to determine the rank of the matrix.
Yes, we're gonna get into that in a bit, yeah.
Yeah, so ultimately, what you focus on is the number of pivot columns that you have, and if the row is all zeros, then it clearly is not a pivot because it's all zeros. So it'll turn out that that's the important thing, is that it doesn't have a pivot, not so much the fact that it's all zero.
Okay.
So it's really actually more the columns you care about than the rows.
Okay, thank you.
Yeah, also. Any other questions?
Yeah, could you please point on the screen? Your pointer's not coming through.
I think there's one online.
Okay, what's the question?
I don't know if you have
I can.
audio.
Yeah, I
You
can.
can't? Okay. I'll turn on audio. Sorry, can you repeat your question, Timothy?
I think that might be me, actually.
I think there was just a request to point to the equations, particular equations that you were referring to, Liam.
I'm sorry.
Yeah.
Okay. Sorry, can you repeat that?
Yeah, if you could highlight,
You don't have any.
like
I
circle,
don't, but I don't have
point
both.
out
Okay.
the particular
Okay.
equations.
Okay, I'm sorry. Can you repeat that one more time?
Would it be possible for you to highlight or circle the particular portions of the equations, columns, rows, pivot tables, etc., that you're discussing at the point that you're discussing them? That would make it a little bit easier to follow the slides.
Of course, yeah. So this is a pivot column. This is not a pivot column, right? Because this can be anything.
We're not
It's
seeing the screen. We're not seeing your screen. We're only seeing you.
Wait, we see.
I think he unshared when he was turning his audio on.
because it gives us like weird screen when I'm presenting that I can't get out of. Anyways, yeah. So this is a pivot column. This is not a pivot column. And you could also say that, this pivot column, you could multiply this entire column by -2 and get this one. So it doesn't actually, this column right here doesn't say anything new about, any information. So that's kind of the important part, is that we have these pivot columns. Does that make sense? Okay, cool. So I'm going to keep my audio on. I can't read the chat, but I can get audio. Okay. So, groups, essentially. So we alluded to this a little bit earlier. Basically, groups consist of a set, G, and an operation. And this can be multiplication, addition, scalar multiplication, basically like anything. And a set G, which can be, natural numbers, or it can be m by n matrices, or it can just be, vectors. It can be a lot of stuff, basically. What a group has to have is it has to have closure. So we mentioned that earlier. Any, multiplication or any result of that operation has to be in the same set as its parts. So for all x and y in G, x times y needs to also be in G. And then we have associativity, which it doesn't matter what order the operations happen in, they lead to the same result. We have this idea of the identity, right? So x, multiplied by e equals e multiplied by x equals x. And then we have the inverse, which is there needs to be something that you can multiply by every element and get e or 1 or whatever it is, this neutral identity element. There's also a special type of group, right, which is called an abelian group, which just means that it's also commutative. So the group of m by n matrices is not commutative. So it is not an abelian group. Groups, they're not really used too often in machine learning, but there are some applications in computer vision. Like for instance, for like rotation, translation, and scaling, you want to kind of handle this with group theory sometimes because the commutativity of it is actually important, as well as like, some other aspects. This also says a little bit about the reversibility of certain transformations, but we'll get into that in a little bit. So the next thing I want to talk about are vector spaces. So vector spaces are kind of a group. There's actually two operations that exist. So, you have a set of vectors. And vectors are typically one-dimensional, but you can actually do the same thing with an n by m dimensional matrix as you would for just like a vector that is n times m elements. It's computationally, it's pretty much the same thing. So when we say vector, we can mean one or multidimensional. It has two operations that you can perform on it. One is addition, and the other is scalar multiplication. So addition has to be an abelian group. So closure, associative, neutral, inverse, and commutative. So basically, scalar multiplication is distributed over addition, right? So what I like to think about this is vector space, or just a vector space, goes through 0. So that's kind of one of the important parts here, is that it has that neutral element that is 0. And it's basically, you can, where addition and scalar multiplication holds. Scalar multiplication, let's see. Addition is an abelian group, but scalar multiplication is not. And if you can kind of think about that, it actually violates closure. As in, when you're doing scalar multiplication, you're multiplying it by a number, you're actually multiplying it by something outside of the set. So it violates that. And also, because there is such a thing as a 0 vector, which is just all zeros, there's no inverse of scalar multiplication. So that's not a group. There's multiplication, just multiplication isn't really defined all that well. You have, there's 3 possible definitions. You have array multiplication, which is basically just element-wise, multiply each element in the vector together by its, constituent pair. You have the outer product, which basically returns a matrix. And then you have the dot product, which we'll get to in later chapters, which basically just returns a number, So the last thing is here is that we have this idea of a vector subspace. And basically it has to have closure under addition, and 0 has to be in it. So it has to basically be a vector space that has, the same kind of closure under addition and goes through 0.
William?
Yeah.
If you go back to that slide for a second. I just wanted to add briefly, in terms of motivation, if we just look at the very top of Liam's slide, where it has the 3 lines under the definition of a vector space, okay? So if you just say, my elements are any tuple, that's basically a vector, okay? Could be a pair, could be 3, could be 512, could be a million long. And you have 2 operations. Addition, like we normally this is no longer an abstract plus. This is just like regular everyday addition that we're used to, okay? And scalar multiplication, which again, this is no longer abstract. This is everyday multiplication like we're used to. 3 times 3 is 9. If you just have those 3 conditions, that actually defines something that's very interesting, that basically the rest of today's slides is going to be a whole bunch of properties that fall out of just having those 3 conditions. That turns out to be incredibly useful for solving various problems. It'll link back to the system of linear equations that Liam showed at the beginning, and it's going to link forward to a bunch of other things. So I would say that's the key motivation, and that one could say that today's topic, linear algebra, is the study of vector spaces. So you really only need those 3 things to have an entire branch of mathematics.
That's really cool. That's very interesting. So a couple of examples of vector spaces is, we can think of Euclidean space as a vector space, right? And so, it's addition and distributive over scalar multiplication. We have matrix space, which is, as we kind of just mentioned, it's actually pretty similar to Euclidean space, but, it's kind of how you denote it. And then we have polynomial spaces, which also add in the property of exponentiating each term. So that is also a vector space. And then a bunch of function spaces, which we're not going to talk about yet, but stuff like, continuous functions, similar to polynomial spaces, Hilbert, Fourier, Sobolev, Banach, which we're not going to get into at the moment, but just to keep in mind, those are also vector spaces. And then it's unfortunate that this got cut off, but the null space is actually a subspace. AX equals 0 is a subspace of Rn, but the particular solution, AX equals B, is not necessarily a subspace of Rn. And the reason for that, I could kind of let people think about that. But one, it's not closed. If you have multiple solutions for AX plus B, then they can add up to be something else. And then the other thing is 0 is not necessarily in AX plus B. So unless B equals 0, or it is homogeneous. Yes. So just to keep that in mind. So when we want to define a vector space, or we want to define what a vector space is, how to work with it, how is one vector space different than another one, what we have to do is start with linear independence, this idea of linear independence. So, and what is a linear combination? So if two vectors are a linear combination of a third vector, we can say that they can multiply together they can be added to each other, multiplied by some kind of scalar, and equal that third vector. So in essence, they can combine to be that third vector. And in some way, if they are linearly independent, then the only solution to that is the trivial solution, which is 0 when it comes to lambda. So you can imagine that, they do not affect each other at all. You cannot add those two vectors up to get the third vector at all. It cut that off too. So basically what you can do in order to find out if how you find out if vectors are linearly independent is you write each vector next to each other as columns. And that's the part that you can't really see here, is each of these columns are a vector. And then you reduce that to row echelon form. So if and only if there are no non-pivot columns, each are a pivot column, then it is linearly independent. And I believe this also means it has full rank. No, full rank? That means it has full rank. I think.
Sorry, I was.
That's fine. Never mind. I'll talk about that later. Anyways, yeah. So it's linearly independent if and only if there's no non-pivot columns. Every non-pivot column you can think about as a degree of freedom, right? So an extra degree of freedom. So if there's no non-pivot columns, then they are they aren't dependent on each other essentially. Yeah, so linear independent kind of leads us to this idea of basis, right? So basis vectors are what's called a generating set, and they have to be linearly independent from each other. And every vector in a vector space can be expressed as a linear combination of vectors in this generating set, which is A. You can, so this kind of defines the vector space that you're working with. This also leads to, say, coordinates as well. But first, like a B is, which is a set of these basis vectors, is a basis of V if and only if, B is not equal to 0. One, you can't have 0 vectors in there. And then this generating set B is the smallest generating set of V that works. And adding any more vectors on top of that would make it linearly dependent on each other. Basically, like, so now this is, for instance, the standard basis of R3, right? So you could define every single vector in R3 with, a combination of these 3 vectors, 1, 1, and 1. Now, this is just as valid as non-standard vectors. Maybe this is -1, 1, 1, or something like that. As long as they're linearly independent, and they are the minimal generating set, then they are a valid basis. Basically, this is how you define coordinates as well. So each vector space could have a different set of coordinates, right? And so when you transform one into another, as we'll see, so that's how you define basically like the basis of a vector space.
Yeah, can I add a little color here?
Yeah, of course.
Yeah. So what we're going to see in these vector spaces, the vector spaces are kind of an abstract concept. And so let's say you defined something that it's usually easiest to think of them in terms of geometric vector spaces, right? So like a 2-dimensional vector space, I just think of as like your typical plot with an X and a Y axis and Cartesian coordinates and all that, like a giant piece of paper. And 3 we can think of in terms of 3D space for the 3rd dimension, Z, whatnot. But so it turns out that, let's say you had a 2D vector space where you're doing like real estate, you're doing a map or something or whatever. It really doesn't matter whether you do the map in miles or kilometers. The properties are essentially the same, and a property that's square will be square, and a property that's rectangular will be rectangular, and it will be triangular. So all you're really changing is the scaling on your basis. Okay. It turns out that you don't even have to use coordinates that are at right angles, like Liam was saying. You could use a different pair of bases. And a property that's square is still going to be square. Other things are really going to be preserved. So then the question is, if you could use different bases and you get different numbers, but things are sort of the same, then what are some of these like irreducible things? And so it turns out that this idea of the basis, how big is it, is one of these irreducible things. That you could say, I'll change my X to meters and I'll change my Y to kilometers, but you still have to have 2 of them. That's the thing that you can't change. So we're going to find that there's a lot, as we get to the very end of the chapter, there's these transformations you can do between different vector spaces. And if this size, which we're going to end up calling dimensionality or rank, is the same, then that means something. And if the size is different, then there's things you can and can't do to go back and forth between them. But otherwise, you can kind of stretch them and rotate them and look at them differently, and they're still sort of the same. So that's why this concept of basis ends up being super duper important, because this is one of the things that you can't change. You can change from feet to meters, but if it's 3D, it'll always be 3D. If it's 2D, it'll always be 2D. And that means that for 3D, you need 3 basis vectors. You can choose different ones, but you always need 3.
Absolutely. And yeah, of course, like a vector space can only have like a finite number of dimensions. So even though that remains the same, the meters or the feet, it doesn't matter what, that they'll still have the same properties. So yeah, what he said, except less eloquent. Anyways, so this is the, moving on to the idea of rank. So rank is basically, where we have number of, say, features. Rank is actually more like how many of those columns actually matter. So we have, these are the number of linearly independent columns or rows in a particular matrix A. So remember when we reduced this to a matrix to row echelon form, each of the non-pivot columns would be a each of the pivot columns would be a linearly independent column. And each of the non-pivot columns would be linearly dependent. So in that example in the slide a while ago, right, even though it has 5 columns, there's 3 pivots, so that would have rank 3. So, and this tells us the number of independent equations that we actually need to describe the system itself. And one of the examples of that being used in machine learning is LoRa, where you have very large weight vectors for these LLMs being encoded into lower dimensional space, because it turns out that the rank of these big weight vectors is actually lower than the number of features used to express it. Just something as a little aside. They mention this in the book, but we'll get to determinants later. If a square matrix has full rank, the determinant is equal to 0. Rank. Now, when it comes to, linear mappings are basically how you get from one vector space to another vector space, or to the same vector space. It's a transformation that you apply to every vector to move it in a specific way. It's considered linear, or it'll also be called a homomorphism, if and only if it preserves vector addition and scalar multiplication. So vector addition is distributive, and scalar multiplication is associative. So that is right. So in other words, for all x and y in the vector space V, for all lambda and phi, which are just real value numbers, then basically this equation holds. So you just pull out the lambda and the phi and distribute the linear transformation over x and y. So basically that's the combination of the first 2 properties. There are 3. There's a lot of ways that we can describe them, but a lot of the ways you're going to hear it described in, say, papers when it comes to mappings, which can also be referred to as like transformations from one matrix to another, like vector space to another. You'll hear injective, surjective, and bijective a lot. So injective is sort of like a one-to-one mapping, So an example of something that is not injective is x squared. So for multiple values in V, if we're transforming from V to W, right? For multiple values in V, if you do x squared, it's going to yield the same result. -1 and positive, or -2 and positive 2 will yield the same result. So x squared is not injective. Surjective, basically, that means that every element in W, in the the thing you're transforming it into, the vector space you're transforming it into, can be reached by a mapping in V. An example of something that's not surjective is the square is square root. Yeah, you can't. Because you is it square root? Yes, it's square root. Because you can't actually reach every element in W if you square root. No, it's not square root, is it? Yes.
Well, like square would be an example in terms of going from reals to reals, because if you square the first number, you're only going to get the positive numbers if W is also the reals, you're only going to get the positives. You're not going to get all of them. So
yeah,
you're effectively getting only only reaching half of them.
Yeah.
Whereas just doubling a number, then you can get to any other real because some other number, when you double it, is going to be any given real number.
Absolutely.
So like simple, just 1D examples.
Yeah. So surjectivity is important for certain machine learning algorithms like GANs, generative algorithms, because when you're training, say, a GAN, the generative function actually needs to be surjective. That means that, so if you have like a bunch of distributions in as the targets, right, you want to make sure that every element in that vector space can be reached from that mapping. So the generative function actually needs to be surjective at that point. And then bijective is injective and surjective. So there's a one-to-one mapping, and you can hit every element in the target space. So if you can imagine, that means that it can be undone. It has an inverse, right? There's, same amount, it's a one-to-one mapping, and it contains all of W. So there's no duplication. So bijective is injective and surjective.
Can we pause here?
Yeah, of course.
So there's two things. So one is we've shifted gears again, and we're now talking about a new topic, linear mappings, okay? So we started with systems equations, then we got the vector spaces, now we're talking about linear mappings. And it might seem like, oh, you're talking about three different things, but they're gonna all come together, right? But the other thing I just wanted to share is like, I don't know how it is for the rest of you, but I, for whatever reason, really have trouble remembering what the heck is injective, what the heck is surjective. It's not intuitive. And even when I have the definitions in front of me, sometimes it's really kind of hard for me to have an intuition.
You need some drawings, sir.
Yeah, so I thought maybe this would be a good place to pause because I know every time I do this, I have to like really pause and say, what exactly does injective? So could something be injective but not surjective? Could something be surjective but not injective? Could something be neither? Could they be right? So maybe this is a good place to see if people have questions.
That's a good point. I mean, the way I'm remembering this is exactly the same. Like, there would be no way I'd remember this if I wasn't doing this presentation. But the way I remember it personally is injective, x squared is not injective, and surjective, square root of x is not surjective, because the square root of x, right? You cannot hit -1 or -2 in W. That cannot equal -1 or -2, getting from V. So you can't hit everything in W. So that's how I'm remembering it, is injective, x squared, surjective, square root at the moment, personally. But yeah, maybe go some questions and stuff. Do we have any?
Anybody have any specific questions they want to raise? So I'll throw one out. If you go from V to W and it's injective, does it have to be injective in the other direction?
It's bijective because both directions.
That's right. So I don't know if you could hear. It's bijective if it's both directions. So the answer is no. In general, not everything's bijection. So x squared, which Liam was mentioning, goes from every real number to all the positive reals. Okay. Sorry, Liam, it's actually not a great example.
Fair enough.
Positive reals.
Sorry.
But as just a general function thing, okay? So this would not apply to vector spaces because they require the properties. But as a function thing, because you see this in math elsewhere, okay? So you can go from all the positive, from all real numbers to positive reals, but you're not going back. So that's an example of a function that doesn't, work. Let's say, whatever, like I said before, multiplying by 2, that's something that very clearly has reverse direction, which would be multiplying by 1/2. And so in that case, that function is going to be both injective one way and injective the other way. It's surjective both ways because you can get to every real by doubling, you can get to every real by halving, and therefore it's a bijection, and so it's injective and surjective both ways.
Yeah, actually it's happened. Subjective must be injective. If it is subjective, this must be injective. Right?
See, this is where I get tripped up. No, surjective does not have to be injective. It does not.
Subjective.
Yes.
It can cover, yeah, it can cover twice.
Yeah. So if you map every point in R3,
You don't need to.
so actually, let's do this simpler. Every point in R2 just to its x coordinate by just dropping the y coordinate. You're mapping many, many things into a smaller number of things. It's fully onto the x-axis. So you can get to every real number by mapping everything in R2 onto R just by dropping the y coordinate. So it's surjective, but it's not one-to-one. Maybe I got the example.
No, it's subjective. You don't have to have all the connections, right? There might be elements that are not connected at all.
If it's not surjective,
No, if it is surjective. There might be elements in the set which are not connected at all, right?
Not for W, like the output. For V, there are things that could not or might have duplicates. Like I think what Ted's trying to say is like if you have like a real space of like 3, or you have 3 rows, 3 columns, you can map that to a space of 2 by 2, and you can hit through some transformation everything, every possible number or every possible matrix in that 2 by 2 configuration space or vector space, but you can't map it back to like a specific value in that 3 by 3 space because you'll need to like add stuff up, etc. Like one of the examples that I found somewhere else is like, like you add 2 of the columns together, 2 of the values together, and then the other one is something else. So if you add 2 of the values together, that could be multiple values in R3,
Right.
but one value in R2.
Yeah, exactly. But there might be some values in set A which are not connected to set B. That's what I'm saying. I mean, there might be some not connected elements.
Not necessarily.
It's not necessarily, but it might be, right?
Yeah.
Might be the case. It's not necessarily all the connections between them.
Yeah.
So I'm not quite sure what you mean by
You know what I'm
connection,
saying about the stats?
because if we're talking about a mapping,
Mhm.
everything in our source will be mapped to something.
Okay.
The mapping is always a complete mapping. So then it's just a question of whether it maps to everything,
Oh,
which
yeah.
in the chat somebody said, I think we also use the term onto, which is a little less jargony than surjective. So like when I was in high school, I think we said onto. But I guess the technical proper term is subjective.
Projected 1-1
So it's like 1-to-1 and 1-to-many, right? It's like easy to say.
Not one to many, but many to one. Because you can't be one to many. A mapping is always only to one, I believe.
Okay.
But someone correct me if I'm wrong. 'Cause like I
was
said,
thinking it might be one.
I always have to take 30 minutes every time this topic comes up.
It might be a good exercise to actually sit down and for each of these properties.
Yeah.
Draw a function, draw a graph of a function.
Right.
Is injective and one that's not injective.
Yeah, exactly. And so it's right. So the hard part is if you just see an example of something that's injective, that doesn't tell you what's not injective. So yeah, great point. Like to have examples of things that are, and then you can combination something that is injective but not surjective, something that's both.
There's actually a diagram a couple of slides later that
Yeah.
might actually help. It's not actually using the same concept, but when we talk about kernels and images, the same diagram might be able to sort of help make this a little bit clearer.
Yeah.
Also, the rank nullity theorem might also help a little bit, but yeah.
So if to try to wrap this up, at the end of the day, remember how I was saying, like, if you have 2D map, whether you use the basis of miles or kilometers, or whether you actually didn't use 90-degree coordinate, you use funny ones or whatever, okay? There's going to be a bijective relationship between the way you represent this square plot of land on a map, no matter what your coordinate system is, if you're using a valid set of basis vectors, because there's a linear mapping that will translate from any one set of coordinates to another. So simplistically, if you say there's like approximately 3 feet in a meter, if you do a map in meters and you do a map in feet, you just multiply by 3 or divide by 3 to do the linear translation from one set of coordinates to the other. There are more complex transformations, but that's what we're going to see, is this idea of, does a linear mapping exist, or does a linear mapping not exist? Does it exist in one direction? Can you also create a linear mapping in the reverse direction? So these are some of the properties that as Liam keeps going, are going to connect this back to vector spaces. So sorry, Liam, for kind of a rabbit hole.
Listen, I mean, like, honestly, the way that this book kind of talks about these topics is also somewhat sporadic, to be honest. Like, having to take some time with, like, you know, alternate sources and trying to put them together is oftentimes the easiest way to digest them, unless it's all reviewed, yeah, of course. But yeah, so injective, surjective, bijective. There's also the idea of, you know, more terms, I know, it's great. We have isomorphism, endomorphism, and automorphism. So remember that a linear mapping can also be described as a homomorphism. Well, what also matters is, are we mapping to the same vector space, or could it be considered the same vector space, or is it a different vector space? Like an example Ted gave is, you know, are we mapping from R3 to R2, where, you know, 3 dimensions to 2 dimensions or something like that. An isomorphism is a linear and bijective, you know, transformation, which, you know, and there can, so linear and bijective. Basically, vector spaces, 2 vector spaces are isomorphic, both linear and bijective, if and only if they have the same dimensions. Now, the basis vectors can be different. They can have different, you know, scales to them, but the dimensions have to be the same. And that should kind of make sense, because there's only one value in V that maps to W, and everything in W needs to be covered. So necessarily they have to have the same dimensions. For endomorphism, we have a linear mapping from V to the same vector space with the same bases, and it's linear, but it doesn't have to be bijective. And then an automorphism is linear and bijective to the same vector space. So yeah. And isomorphism, I've seen that in many papers before. So the transformation itself, we can actually talk about in terms of this transformation matrix, which we refer to as A with that Greek character there, which I believe is there. That's how they refer to it in the book. So if we're talking about A being a transformation matrix in the space of the real numbers m by n, we have a series of basis vectors with a series of basis vectors B, and then, like, you know, any x or any y in V, where x is in V and y is in W, then you essentially multiply this transformation matrix by x to get y, essentially. And this also formatted a little bit incorrectly, but you can kind of see it as, like, a transformation is occurring to each one of these basis vectors. This is another way to kind of represent it, right? For each one of, if this is like, you know, the different basis columns or basis vectors, then that's one way to kind of conceptualize it.
So I don't know if you have any more slides on the linear mappings. So there's a sentence in the book, I don't remember exactly where the authors say it, but they introduce matrices as a shorthand for a linear system. Then they say you can also use a matrix as shorthand, so to speak, to represent a linear mapping, a transformation from one vector space to another vector space. And why linear algebra is a often studied field within math is because it turns out that every property of matrices that makes sense as a transformation matrix also makes sense with a system of linear equations. That a matrix is a matrix is a matrix. So you could have actually come up with a system of linear equations and gotten this 3x3 matrix and said, this represents my system. And if you treat that as if it were a transformation matrix, everything still works, everything still applies. Any kind of, now, there may not be the exact same meaning of what something is, but if you talk about anything we learn in this chapter, the rank, the null space, the this, that, they have direct analogs, whether you're talking about a linear mapping or system. And in fact, basically that's why we use linear algebra, is because this idea that a matrix has these mathematical properties, we can study them, and once we figure out an interesting property, we can then map that to all the places where matrices represent things. You figure out a way to use a matrix to represent adjacency lists in a graph. Every property we know about matrices applies to that adjacency matrix. The determinant that we're about to talk about, all these kinds of things. Eigenvalues, they apply to linear equations, they apply to transformations, they apply to graphs. So that, just to kind of give more color, like that's where all this stuff connects, because matrices end up being incredibly useful, and so you can study it in one place and then try to connect it to everything else.
Yeah, I think I'm actually going to steal the idea for graph adjacency lists there. I thought of it like that. Yeah, so that's a good description of that. As far as like basis change, this is the next, basically the section in the chapter. And this just answers the question, basically, what happens to that linear mapping if you change the basis of V or W. And the way to think of it is relatively simple. Remember how we defined that A to be, you know, a transformation matrix, and we apply it to, you know, everything. Or if we transform like a series of basis vectors into a new basis. For V, we're going to call that transformation matrix S, and for W, we're going to call it T. Now remember again that V is the input and W is the output of the vector spaces in this transformation. We can actually think of it like this. If we're considering that A1 is the new transformation matrix, which describes this linear mapping, and A is the old one, then we can take the inverse of T, multiply it by S as well. And the way you can kind of think about that is because T is the output, it can actually go on the other side of the equation. So you could say T times the new transformation matrix equals A times S, which is the change of the, you know, the old, or the change of the, you know, the input, and T is the change to the output. So in this case, that's kind of how I remember it. In this case, A1 and A are equivalent. In this case, they are equivalent transformations because, you know, certain properties, they can be transformed into each other. If A1 and A are similar, you know, then you can actually say that the same matrix is the change in basis for V and the same change of basis for W. So that means that A1 and A are similar. So this is a slide I think might help kind of clarify injectivity and surjectivity a little bit. So this is the idea of the image of the kernel. So I talked about the kernel being the null space, right? So if you're thinking about that in the left sort of oval as V, and then the inner part, let's see if I can actually do it this time. Inner parts of this are the vectors in V, or the solutions in V that map to 0 in W, right? So this is AX equals 0. And really quick, so, okay, let's talk about the image. The image are the vectors in W that are reachable by the transformation, right? So you can actually think of this image, right? If a transformation is surjective, then the image contains all of W. If it's and the bigger that image is, the more surjective it is. Let's see how to describe injectivity here. Oh man, I'm not entirely sure. Yeah, it's hard to talk about injectivity here. Basically, if you have 2 points that lead to 1 point here, then it's injective. But that's a little bit hard to visualize. So that's just for surjective, I suppose. But kind of helpful to show the transformation sort of like this. And so so the image of a certain transformation is basically just the entire vector space transformed. Pretty much the same thing. So the rank nullity theorem is actually a very interesting property. Very interesting property of this, which is that the dimensions of the kernel plus the dimensions of the image equals the dimensions of V, or the dimension of the domain. Kind of a way to think about this is like, the greater the kernel, the more uncertainty, or the greater the dimensions of the kernel, the more uncertainty you have. Like the more of the vectors, or the more non-pivot columns you have, the more degrees of freedom you have. So the kernel is the uncertainty of the transformation, I would say, something like that. And the image is more like what you can hit with that transformation. So if you have like a greater dimension of a kernel and a less, the dimensions of the image are less, then it is less injective, and you have more independent columns. Whereas if the dimensions of the image are greater, then it's actually more surjective. And of course, because more of the output space is being taken up, right? So yeah, you can reach more of W. So yeah, just that there's that kind of inverse relationship there. So
yeah, and if I could again add some color here. For me, I always found the geometric intuition on this to be relatively simple. So if you have a system of 3 linear equations, we can picture that in 3D R3 space, right? If your image, if your kernel is dimension 1, then your set of solutions is going to be a line. And in plain English, we talk about a line being a one-dimensional object, right? If your kernel is 2-dimensional, then it means that your solutions, if you map them, plot them, they're going to look like a plane. And if you have high school geometry, we all kind of talk about a plane as a 2-dimensional object. And that they have to always sum up to 3 is, at least for me, was always kind of like a relatively easy thing to understand and stomach. It's not some highly, you know, abstract idea that they always add up to 3.
Seems like a completeness, right? Like a completeness type property.
Yeah, exactly. Completeness. It's like, it's either, actually, Liam, I think, said, it's either, you know, your degrees of freedom or your degrees of specificity, and they always add up to 3.
Yeah. And like the way, like if you have like 2 non-pivot columns or 2 more degrees of freedom, you're going to have that plane because 2 of the dimensions do not matter, you know? So like, and null space is greater and it is 2-dimensional because 2 of the variables, you can put anything in there. So,
Right.
Yeah.
But for me, like, when you say null space, it's a lot easier if I just think of a plane. That's like all the solutions are valid. If it's 2-dimensional, it's a plane. And in the case of things like this, they always go through the origin. So the lines or planes are never off to the side. They're always centered. They're just rotated in some way around the origin.
Yeah. And then if you have full rank, so if your matrix is full rank, so you have no non-pivot columns at all, the null space will be 0-dimensional, right? Because you won't have, it'll just be, you know, point at 0, right?
Yeah.
When AX is 0. Yeah, okay. Anyway.
So can you give an example of a system of equations that would be 0 kernel?
Well, yeah, I mean, if in reduced,
Sorry, the other way around.
if,
Gotcha.
oh, I mean, well, yeah, you'd be like, you know, okay, so there's row echelon form. I did not talk about reduced row echelon form, which is not only are all of the columns pivot columns, but the rest of the values are 0. So in this case, if you had, like, similar to the basis vector, the canonical basis vector I showed earlier, so if you have basically the identity matrix on 3-dimensional identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1, that's a system of equations that has no degrees of freedom, right? So that would have or that would be, you know, 0 equals 0 and nothing else, right?
Yeah, so if you have that, then your let me get my terminology right. Your image is 3-dimensional and your kernel is 0-dimensional.
Yeah.
If you want an example that's the opposite, where your image is did I say that right before? See, this is again one of those things that, like, I have the intuition, but using the terminology right, sometimes I get tripped up. So if you want to have a 0-dimensional image and a 3-dimensional kernel, basically that means your matrix has to be all zeros. It can't have any pivot columns. So it's like a degenerate case that the only way I can represent it is just to say, what values of x, y, and z satisfy the equation 0 equals 0? It's like any values. That's why you get all possible real solve this equation, but it doesn't look like a normal equation.
Yeah, totally. So like in that case, the kernel would actually take up all of B, because again, it doesn't matter, and it would all map to, you know, a 0, which 0 vector. So the 0 vector would be the only thing that is reachable from B.
Yeah. So in real world, you're probably never going to encounter that situation, but if it has a unique solution, then you can have a kernel that's 0-dimensional, and if it has a solution that looks like a line, then it'd be 1-dimensional and so on and so forth.
Before I go on to affine subspaces, etc., which will be the last slide, are there any questions pertaining to image, kernel, rank, basis, etc.? Anything? Anything in chat?
We're good.
Cool. Okay, last slide is affine subspaces and mappings. So the difference between linear mappings and affine subspaces in machine learning is oftentimes interchangeable, but they are distinctly different. So remember, for linear mappings, I said that it has to, go through 0, and therefore it has to have a neutral element, and it has to satisfy those conditions. Well, an affine subspace is essentially a transformation of a vector space by a vector. So that's kind of a fancy way of saying you just add a vector to a particular subspace. In this case, right, there's a lot of, math, but hopefully we've kind of kept up to the point where we can read it, if you couldn't already. With a vector space, right, with V, vector addition and scalar multiplication, an x0, which is a vector within V, and where U is a subspace of V, then L, this affine subspace, is basically x0, this vector, plus U, which is equivalent to x0 plus U, where U, for every U in the subspace U. And then, for every U that, actually, I'm not even going to talk about that last part. That's from the book, honestly. If I'd like, I'm not going to do that part, but you see what I mean? Like, it's just a transformation on by a vector. So it doesn't go through the origin. X0 in this case is called the support or translation point, and U is the direction or the direction space. Another way that you could actually write this is for all X within L, this affine subspace, X equals that translation point or vector, plus a series of scalars on the basis of U, on the basis vectors of U. So these lambda scalars can actually be parameters. So that's how you kind of turn this into a parametric equation, which in some computational circumstances is easier to digest. And then we could say actually that the solution to AX equals B is an affine subspace of Rn, and it has a dimension of n minus rank A. I'm actually going to open this up. Does anyone want to explain why that is true? Can anyone explain why that is true? Okay, I'll explain why that's true. All right, so basically, it doesn't go through the origin. It's an inhomogeneous system of equations, so it doesn't go through the origin. So it is an affine subspace. It's a translation of Rn by B, I think. Where B is actually the support translation point. And it's of dimension n minus rank A, because where n is the, because again, we're talking about that line or that plane, that is the set of possible solutions. So where the rank of A is the number of pivot columns or certain columns that we have, n minus rank A is the number of uncertainty or degrees of uncertainty we have. So it's an affine subspace because it doesn't go through the origin, and it is translated by the vector B, and it's with the dimension of the degrees of uncertainty of that. So. And then the last concept that I want to talk about is an affine mapping. So basically, it's just we're basically saying that this is a transformation that is also added on to a vector, and this is technically actually what a neural net does. Which Ted, actually, if you want to talk about what you mentioned earlier about like how an affine space is technically what a neural net does, or a neuron does.
Yeah, briefly, since we're past time. So pretty much every neural network module that you have, whether it's a simple one, fully connected, or something else, is going to take the input and it's going to multiply by matrix. It's going to do a linear transformation on it. And so you can really think of it as mapping a vector that comes from some input vector space to an output vector space. If you kind of dig a little deeper, you'll see usually there's the option to have a bias vector. So you don't just do a matrix multiply, you do a matrix multiply and then you add. And so like Liam's saying, every time you just add a vector and you're no longer centered around 0, but you're centered around some other point, technically it's an affine space, not a vector space. Mostly in machine learning textbooks, you're going to see the word linear used. You're almost never going to see the word affine used. People are just not being rigorous. Okay, they should be using the word affine. It's never going to change. You're going to see linear everywhere for forever. But from the math perspective, technically, what they're talking about is affine spaces. And I mentioned to Liam, one of my personal interests is like model interpretability, and in particular for LLMs, these large transformer model interpretability, and they are residual networks where every layer is not just taking an input and producing an output, but its output gets added back to whatever its original input was. And so if you think about this, people think about it in terms of imagine like a computer bus. You have this residual stream where the values are on there and each layer just keeps summing onto it. And if you want the numbers to keep getting bigger, you just keep summing more things. And in theory, if you want them to get smaller, you can put negative numbers in, and when you sum those, then that'll actually pull things in the other direction. But so then there's this concept that if there's this one residual stream that connects all the layers, is that actually a single vector space, or more properly, is that a single affine space? And then can we find meaning in that? So if you were to go a particular direction northeast in this obviously very high dimensional space, like 4,000 or whatever, but does that actually represent maleness versus femaleness? And does some other direction represent how blue something is, or how red something is, or how smart a person is, or how big an object is? And so it's probably not absolutely necessary that you really think about all this linear algebra math if you're just using a neural network or something like that. But we will see in part 2, when they go through examples, that definitely this math underlies a lot of the calculations in linear regression, in support vector machines, things like that. And so that's sort of the point of this book. It's very technical. The exercises are very mathy. They're not very engineering. Prove that, blah, 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 things like that. But hopefully the deeper we understand these concepts, the better intuition we'll have, not just on how the algorithms work, but also maybe what their failure modes might be. Like, why is it that I should be careful if I'm doing a linear regression and I have 2 inputs that are somewhat collinear, they're very similar. So if, if you had annual income and total wealth, those two tend to be super highly correlated, okay? If you make a lot of money per year, you probably already have a lot of money, If you have both of those inputs, that could be a problem if you're doing linear regression. And so you have to kind of boil it down to some of this math to understand that. Otherwise, it's just memorization in general.
Yeah. And like one more thing is, like, you could, now correct me if I'm wrong, but you could use like the rank nullity theorem to say, like, hey, I'm training a generative network. I need it to hit everything in W, or the output space. So that means the kernel or null space needs to be 0, which means my transformation needs to be close to full rank, right?
Yeah, that's the understanding. Unfortunately, if you look like a GAN, nobody really knows the transformations. So we know theoretically that's what we need, but it doesn't necessarily help us. But people who are smarter than me do think about this and they think about ways to constrain the process to like what you're saying, to try and get like full thing.
So anyways, that's all I got. This particular one has been, I decided to, I put this in a kind of a more declarative way, and we went way over time, so I apologize for that. That's just because I figured, that maybe not everyone had a chance to, read the chapter beforehand. But I think, moving forward, maybe these might be a little bit less declarative or not, it depends. There's a lot of information to kind of condense in a way where in like an hour or an hour and a half. So, with that in mind, are there any closing questions from anyone?
Yeah, thanks, Liam. So I understand some people may need to go if they, plan for a certain amount of time, but Liam and Ryan, if you guys are available, we can stay a little bit longer if there are people who have questions or if there are exercise problems people would like to spend a little longer on. Again, understand people may need to go, but happy to stay a little longer if people have specific questions that would be helpful to talk about.
Yeah. Well, I did some of, I think I did maybe 3/4 to and a little bit more of, the exercises. I kind of flipped over the show questions, or show that this equals that, just because, not familiar with the exact way to do that formally, but they were all, I don't know. Did anyone else do any of the exercises?
I just downloaded the book today.
Hey, that's fair. That's kind of what I was expecting, honestly, because this is the first meeting and stuff. So yeah, that's completely fine. We have.
I looked them up. The thing is, though, that most of them I already studied. So.
What? Oh yeah, there's the answers are online. Is that what you're saying? Because there the answers to the questions. There's actually a repository for them.
Oh, okay.
Yeah, actually, I think we could put that somewhere, but yeah, shouldn't.
Yeah, so I'll say for this chapter, I think it's not super important that you be able to do the exercises literally as the exercises are written. They're pretty mathy, but hopefully you understand, probably the idea of having a basis of a vector space. Right, and that it has dimensionality, and therefore, if the vector space has dimensionality, then your matrix also has dimensionality. I think if you got those couple basic concepts, that's probably really good building blocks for going into the ML applications that we get to later. And then also, just so you guys know, the first part of the book is different topics in math. Fortunately, this is not one of those books where Chapter 5 heavily builds on chapters 2, 3, and 4. You can, not quite completely, but you can largely read every chapter without having read the chapters that came before it. So that does make, even though this book is pretty math heavy, it makes it a little bit more approachable because it's not just constantly snowballing and getting more and more esoteric. It's going to stay at sort of the same pace throughout the whole rest of the book.
Okay. Is there anyone else who wants to add anything? Okay. We can wrap this up then, I suppose. Thanks everyone for coming. Hope you either got a review of something that you already know, or learned something new. Maybe had a new basis vector for your future studies. I'm sorry I said that. I apologize. But you see, so yeah, thanks everyone for coming. Hope to see you at the next one.
Thank you, Liam. Appreciate